This is the lesson video for AP Calculus AB on section 3.4, velocity and other rates of change. And in this section, what we're going to do is get into some really basic applications of some of the derivative rules that we went through in 3.3. Now, what you're going to find in this course is that the primary application that we're going to use when we talk about the relationship between a function, the derivative, or a function and an integral, we're going to talk a lot about motion. So stuff that is really kind of intuitive and things that a lot of you have worked with before in physics classes. So it makes a lot of this stuff easy. One thing that sometimes comes up, though, is people know some kinematic equations that they can use as shortcuts for some of the things that we do. The thing that I want to tell you about that, if you're thinking about doing that when we go through these problems, is that those equations all are derived using calculus. So what I want you to do when we work through these problems is actually work through them using calculus. And then, when you're in your physics class, if you want to use the shortcuts and the formulas that are developed from calculus, that's fine. But in here, let's try to stick to the calculus. So in this section, we've only learned a few of the derivative rules so far. So we're really going to stick to basic derivative rules and just focus on some pretty easy relationships, but start to get into the ideas of problem solving using derivatives. So this first problem, when this section refers to other rates of change, there's a few questions in here where we're going to go through rates of changes of other types of functions. But like I said before, it's primarily going to be position, velocity, and acceleration. So this first problem says a pebble is thrown into a still pond causing concentric circular ripples. Find the rate of change of the total area of the rippled surface with respect to the radius when the radius r is 20 inches or 10 inches and 20 inches. So this is actually really simple to do. The main thing is we know we're talking about the area of a circle. So that would be area is pi r squared. And if I get the rate of change with respect to the radius, this is what they're talking about. So my area is a function of radius. They want us to get the derivative of area with respect to radius. So it's just 2 pi r. And then it says to evaluate those at time is 20 and time is 10. Well, the notation we can use for that, dA dr, and then the vertical bar when r is equal to 10, in this case, if I plug that in, I'm just going to get 20 pi. And then for the second one, dA dr when r is 20 would be equal to 40 pi. Okay, so that's all they're really getting at, is just finding how it's changing with respect to a change in the radius. So pretty simple to do. Now, like I said, primarily we're going to focus on what's below here. So we're going to talk about velocity, we're going to talk about position, we're going to talk a little bit about acceleration. Velocity is just the instantaneous rate of change of the position with respect to time. So primarily when we take derivatives, when we're dealing with motion, really almost exclusively with motion, we're going to talk about the derivative with respect to time. Primarily today, our derivatives are going to be with respect to time, just because we're primarily dealing with motion functions. Okay, so when we are talking about position, velocity, and acceleration, one thing that I want you to notice here, S is typically going to be our position function. That's a common variable that's used in physics. So we typically use S for position, V for velocity, and A for acceleration. But what I want you to notice here is when we talk about velocity, all we're talking about is change in position over change in time, displacement over time. So if I just do displacement over time, change in position over change in time, that's going to give me an average velocity. If I apply a limit to that and now say, okay, let me get the change in position over change in time for an infinitely small time interval, that's going to give me an instantaneous rate of change, or the velocity, which is going to tell me how fast something is moving, and it's also going to tell me which direction it's moving. So remember, velocity is going to be a vector quantity. It's got a magnitude and it's got a direction. So velocity is positive when we're moving forward, negative when we're moving backward. So for now, and really mostly in this class, we're only going to have motion in one direction. So when we start to get into having motion in multiple directions at the same time, we start to get into some vector calculus. It gets a little more complicated, but we're going to keep it fairly simple in this class. When we talk about the magnitude of the velocity, we're talking about speed. So if I just tell you or ask you how fast is something moving, I'm referring to speed. And that's all I want to know is what's the magnitude of the velocity. I don't care which direction it's moving. All right, and then acceleration is the rate of change of the velocity with respect to time. And you can see here, in terms of how do we find this, well, we just take the derivative of the velocity with respect to time or the second derivative of the position function. So here's just a kind of simple relationship that we're typically going to see. Here's my position function, in this case, 1/2 gt squared. Take the derivative of that, we get gt, and then take the derivative again, and we get g, where here we're assuming g is the gravitational constant. Okay, so that's a really common relationship that you're going to see. All right, so what I have here is an example that I want you to try, because most of you have at least some experience with some of these basic physics concepts, and I want you to try this using calculus. Some of these problems are strictly algebra problems, but some of them are going to involve using calculus. So on this problem, you've got a scenario where it says a dynamite blast propels a heavy rock straight up with a launch velocity of 160 feet per second, and it reaches a height of, and then we have this position function, 160t minus 16t squared feet after t seconds. So there's 4 questions here. How high did the rock go? What's the velocity of speed on the way up and the way down when we're at 256 feet? What's the acceleration? And then when did the rock hit the ground? So pause the video, give yourself, 5-10 minutes, whatever it takes, work through the problem, and then when you're done, unpause the video and I'll show you the solutions. Okay, so here's what you should have come up with for that one. For how high did the rock go? That's strictly an algebra question. Well, really, I guess there's a little bit of calculus in it as well. So I want to know how high did it go. Take a look at this graph that we have over here to the side. So think about what would happen when we actually go through and think about how high this thing goes. It's shot from the ground, it shoots straight up in the air, and it's going to go higher and higher and higher. And then for one instant in time, it's going to stop, and then it's going to start moving down. So we want to know when is the velocity 0. So I did actually take a derivative here. I misspoke earlier. I did actually take a derivative and set it equal to 0 and found that that happens, the velocity is 0 when time is equal to 5. So that tells me it took 5 seconds to reach that maximum point. And then I just want to know what was the position at that point in time. Well, the position at time 5 was 400 feet. So how high did it go? It went up 400 feet. Okay, part B, what is the velocity and speed of the rock when it's 256 feet above the ground on the way up and then also on the way down? Well, they didn't tell us what point in time we're talking about. So we've got to figure out what point in time are they referencing. So this is my position set equal to 256 feet. I want to know, when does this happen? So notice we've got this kind of ugly equation to try to factor. Most of the equations you're going to see in this class are going to be equations that you can factor fairly easily. So if you see something like this show up, typically there's going to be a constant you can divide out, and then you're going to be able to factor it pretty easily. So in this case, I can divide everything by 16. Also got everything on one side of the equation, and it's simplified down to t squared minus 10t plus 16. Now that factors into time is 2 and time is 8. Now think about what that means. That means we were at a position of 256 feet above the ground at 2 points in time, when time was 2 and when time was 8. So on the way up, we were at time is 2, and on the way down, we're at time is 8. So now let's look at our velocity and our speed. On the way up, our velocity at time is 2 is 96 feet per second. The speed's going to be the same thing because we're moving up. The velocity was positive, so the speed always has to be positive. On the way down, we find our velocity at time is 8. And remember, we found that velocity function on the previous problem, 160 minus 32t. So I plug time is 8 into that. I get negative 96. That's my velocity, negative 96 feet per second. I'm moving down. And the speed is still positive 96 because that's just how fast we're moving. Part C, what's the acceleration of the rock at any time? That's just the second derivative, negative 32 feet per second squared, very simple. And part D is really pure algebra. When does the rock hit the ground? So when's the position 0? So you factor this out, you get actually 2 points in time. Time is 0 and time is 10. We know time is 0 is our initial time. So that means time is 10 would be the time when we hit the ground. Okay, so let's move on here. And I've got another problem that I want to kind of talk through a little bit. We have a position function here, and it says, first of all, find the acceleration. What's the acceleration after 4 seconds? And then it says graph this. So first of all, let's just quickly go through finding the acceleration. So my velocity here would just be the derivative of the position, which would be 3t squared minus 12t plus 9. And then my acceleration function, which is just the derivative of the velocity, would be 6t minus 12. And they also said, what's the acceleration after 4 seconds? Well, in this case, that's 24 minus 12, or 12. Let's see, what units are we using here? We have meters per second squared. Okay, so the units are not that big of a deal for your solution unless the problem specifically asks you for units. So don't feel like you always have to include them. Sometimes you're going to have problems that don't even give you units. But if I ask you to include units, that will be part of the points for the question. So make sure you check that. All right, so now let's get into really the important part of this question that I wanted to discuss. So graph the position, the velocity, and the acceleration. So that's pretty straightforward. You can see the position is the cubic function, the velocity is the quadratic, and the acceleration is the linear function, just as we knew they were going to look. So that's not really what I want to focus on here. What I want to focus on is part C. When is the particle speeding up and when is it slowing down? So remember, the higher the magnitude of the velocity, the faster we're moving. So that means when the velocity is further from 0, we're moving faster. When the velocity is closer to 0, we're moving slower. So when we're thinking about speeding up, we should be thinking about when is that velocity graph moving away from 0. When we're talking about slowing down, when is the velocity graph moving towards 0? So let's start with speeding up. I'll just go in the same order they went in. So speeding up, let's just look at our intervals here. So I can see on my velocity graph on this interval in here between 1 and 2, you can see how I'm getting further from 0. So even though it's negative, it's getting further from 0. So I'm speeding up from time 1 to time 2. Okay, and then also, when else am I moving away from the time axis? Well, that happens if I look at my velocity graph from time 3 and then as far as this goes. So whatever our end result or end time would be, that's where we would end. So in this case, I guess they give us 5 as the end time, so I can actually put 5 in there. And you can choose to include or not include the endpoints here. It doesn't really make a difference. Whether you include them or not is sort of a debatable topic, so I'll accept either answer. Just realize that sort of interchangeable when we're talking about motion. Slowing down would be the second part of this. Okay, so we're going to slow down when our velocity is moving towards 0. So from time 0 to time 1. And then also, let's see, if I look at my velocity graph, once I pass time 2, from time 2 to time 3, the velocity is moving towards 0. Okay, so that's one way that you can figure out speeding up and slowing down, is just by looking at the velocity, whether the velocity is getting further from 0 or closer to 0. All right, so another way we can do it is by combining information. If we look at the velocity graph and the acceleration graph and the values, you can tell whether something's speeding up or slowing down by the signs on the velocity and the acceleration. So let's look at our first interval. We were speeding up on the time interval from 1 to 2. So what I want to point out here is, take a look at my velocity graph. Okay, so you can see my velocity is negative on that interval. You can also see that my acceleration is negative on that interval. When the signs of those two things are the same, we're going to be speeding up. So if my velocity is negative and my acceleration is negative, you can sort of think of it as the length of the velocity vector is getting longer because the acceleration is sort of working in the same direction as the velocity vector. When those two vectors are working against each other, you're going to be slowing down. So let's take a look at one of those time intervals. So one of those time intervals was, let's say, 2 to 3. So on this time interval from 2 to 3, look at my velocity graph. It's negative, and my acceleration graph is positive. So think about your velocity vector pointing in a positive direction and your acceleration vector pointing in a negative direction. So again, the acceleration is working against the velocity. It's going to make that velocity vector get shorter, which is going to make the speed get smaller. So that's really what we're looking for there when we're talking about speeding up versus slowing down. You can either just look at the graph if you have that information, or you can look at the acceleration and the velocity together, and those two things together can tell you speeding up versus slowing down. All right, so I've got another example here I want you to try now that we've discussed that. This is a velocity graph. It says that up above here. So we're looking at the graph of the velocity of a particle, and there's some questions about speeding up, slowing down, acceleration. So what I want you to do is pause the video and take a few minutes and work through those questions. So go ahead and do that, and when you come back, we'll talk about the solutions. All right, so the first thing I usually do on problems like this when I'm given a graph is I usually label what my graph is representing, just as that kind of constant visual reminder of what the graph means. So this is a velocity graph. So I labeled it as V of t. That way, every time I look at the graph, I remember, okay, this is the velocity graph. Let me make sure I interpret it that way. So we're going to have a lot of problems where we're going to have, you know, the graph of a function or the graph of a derivative or even the graph of a second derivative. And you always want to have it clear in your mind which graph you're actually looking at. Okay, so when's the particle move forward? When's it move backward? When's it speed up? And when's it slow down? So forward and backward are really easy. If I have a positive velocity, I'm moving forward. If I have a negative velocity, I'm moving backward. So that's where those intervals came from. Now, the speeding up and slowing down, what we're looking for, because we just have a velocity graph, are we moving towards the time axis or away from the time axis as we read the graph from left to right? If we're moving toward the time axis, we're slowing down. If we're moving away from the time axis, we're speeding up. Okay, so that's where those solutions came from. When is the particle's acceleration positive, negative, or zero? So remember, the acceleration is the slope of the velocity graph. So if my velocity graph has a negative slope, that means the acceleration is negative. So you can see, for example, on this first interval from time 0 to time 2, you can see I've got a negative linear section to that graph. That means acceleration is negative throughout that interval. Okay, and then when I have a positive slope, obviously my acceleration is positive. And when I have horizontal segments in here, that means my velocity is not changing. It's staying constant. So if my acceleration is my velocity is staying constant, that means my acceleration is 0. And that's where those time intervals from 2 to 3 and 8 to 9 came from. C, it says, when does the particle move at its greatest speed? So this is a little bit hard to answer because we don't have a y-axis or a vertical axis to really scale this off of. But if I look at this, I can kind of estimate it. Whether or not you want to include time as 0 is sort of debatable. But it seems like that point and this series of points down here look like they're about the same distance from 0. So what I said then was time is 0 and time is from 2 to 3. If you included 0 or didn't include 0, it doesn't really make a difference. It would have to make it really clear in the question whether or not they wanted you to include 0. And then D, it says, when does the particle stand still for more than an instant? So if I'm going to stand still for more than an instant, that means my velocity needs to be 0 for more than an instant. And I have 3 points in time where the velocity is 0, here, here, and here, but it's only for that exact moment in time. So it's never going to be standing still for more than just an instant. Okay, and then the last thing that I have here is just kind of a summary as a reminder, because this speeding up and slowing down is something that we're going to use all year long, and I want you to kind of get this in your head. When the signs are the same, we're speeding up. When the signs are opposite, we're slowing down. So this first part, it says, if you're moving to the right, and you're speeding up, then your acceleration is positive. So think about that, because if we're moving to the right, we had a positive velocity, we have a positive acceleration, we're speeding up. The second one, we were slowing down, we were moving in a positive direction. That means the acceleration has to be opposite, it has to be negative. So that's all you're really doing there, is just kind of making sure that you have those clear in your head. The signs are the same, speeding up, signs are opposite, slowing down. All right, so last thing that I have attached to this, I have this, there's a blank page here, but then the next page, there's these concept worksheets. These are not things that you need to turn in. It's just extra practice for you. So you have a lot of these questions in the Math Excel assignment where they're going to talk about position, velocity, and acceleration. You're going to work off a graph. You're going to work from a function and all that kind of stuff. But if you feel like you need more practice, you can use these concept worksheets for practice. So I have these attached to the notes. I also have the solutions for them attached in the same place in Schoology, so that you can check your answers if you want to work through these, but not something that's required. But I would say at least take a look at them, because it gives you just a little bit different presentation of problems than what you're going to see in Math Excel.